This is Dr. Kraus. I'm recording a video of a solution to a quiz we just took in my class. We did not have time to cover this in lecture as I normally would, but I didn't know if this would also be helpful to other subscribers who are learning about sketching Bode plots, and so I'm just throwing this on my YouTube channel. If you're given a transfer function in this form, one incorrect assumption that students might make is to say that because this is in an S squared form, this is in an S squared form, these both must be complex conjugate poles. But we should verify that, especially we ought to be suspicious. This is pretty large compared to this guy, and so this may be an overdamped form that we could then factor into two real poles. So what we need to do is use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a. A is 1, b is 561.6, c is 355.3. So the key issue is if this number turns out to be positive, then we are in fact overdamped, or we have two distinct real roots. And if this number turns out to be negative, then this would be an imaginary number. We'd have a complex conjugate pair of roots, and it would in fact be an underdamped second order term. So I'm going to flip over to Python a second. I've got this ready to go. So if I define A, B, and C as we just discussed, then it turns out that b squared minus 4ac is in fact a positive number, so we will in fact have distinct real roots, and those are the actual root values. So the S1 is a negative 0.6283, and S2 is negative 565.47. Both of those are in radians per second. So our next move, we would want to convert that to hertz, and then those would become, if we take a negative 1 times that, real first order poles. Distinct real roots turn into first order poles. Sorry, I misspoke just a little bit. So if I was just going to double check that by creating I'm creating a Python control module transfer function for the first part and the second part, and then the numerator separately. And so if I just double checked, well, let me show you that. So that is what the transfer function for the first half of this thing looks like on the left. So this guy is den 1. This guy will be den 2 in a minute. So there's den 1. There are the poles of den 1. So we do have distinct real roots. And so if we convert those over to hertz, we're saying that there is a first order pole at 90 hertz and another one at 0.1 hertz. So if I was going to start making a list of my poles for the sake of sketching my Bode later, we're saying there's a first order at 0.1 hertz and 90 hertz. So in the exact same way, I could take this one and write this up as A is equal to 1, B is equal to 9.425, and C is equal to 246.7. Shove that into the quadratic formula. I'm going to go ahead and skip that step here and just let Python do it for me. So just as before, here's the transfer function for the second part of the denominator, so that the overall transfer function will be the product of those two times 8,000 in the numerator. And the poles turn out to be complex conjugate numbers, specifically those, negative 4.7125, whatever, plus or minus 14.98j. So that is negative zeta omega n plus or minus j omega d. And so I want to find omega n and zeta. So I take the absolute value of that pole to find omega n. I would then could verify that that's also the same as just taking the imaginary part squared, real part squared, and take the square root. Divide that by 2 pi. My natural frequency in hertz is 2.5. And then, as I said, the real part of the pole is, let me just write this down because I've said it a couple of times now. We're saying that for a complex pole, S is equal to a negative zeta omega n plus or minus j omega d, where omega d is defined to be omega n times the square root of 1 minus zeta squared. So if I know omega n already. Oh, and we're saying that omega n is equal to the magnitude of S, which you could verify by squaring that and adding them together and making this substitution. So if I know omega n and I know my pole, then zeta is just the negative real of S divided by omega n. So we're doing that here, and we've got zeta and we've got omega n. So we're also saying that there's a second order complex conjugate pole at 2.5 hertz with zeta equal to 0.3. Now, my students and I had a big go round about omega n versus omega d, and it turns out that the peak is at neither of those. And if you really wanted to get specific about the peak frequency, it's at, and there's a 2 here that's different from omega d. And so it turns out that the peak frequency in hertz is 2.26. And the last thing we need to know is what decibel value does this Bode plot start at. And so if I plugged in S equal to 0, I would get this in my numerator and this number times this number in my denominator. So G of 0 is 8,000 divided by 355.3 times 246.7. So if I do that calculation, that turns out to be a little less than 0.1. So in decibels, that's a little less than negative 20. So having a list of the poles, and since there are no zeros, I'm ready to draw this thing. It's going to start off with an initial slope of 0. And we already specified, I'm going to call this negative 20 dB, and so we're going to start off as a flat asymptote. We're going to get to 0.1 hertz, and we're going to start going down at a slope of 20 dB per decade. That should be a straight line, which is a little bit on the weak side there. So that would be my slope there of my asymptote. And then so this is 0.1, this would be 1, this would be 10. My next pole is at 2.5-ish. So if I just continued this thing down like so until I got to here, at 2.5. Then I have my underdamped second order. So in this stretch in here, I'm at negative 20 dB per decade. Then at that point, I would drop down to negative 60. I might not be drawing this perfectly to scale. So here I'm negative 60 dB per decade. And then I would get to that 90 hertz part. So this would be 100, so it would be this guy. So I don't quite have enough room to do what I need to do. And then out here I drop down yet another 20 dB per decade to take me down to minus 80. So not super pretty, whatever. But that's it. And so I would have a little, so if I was going to kind of fill that in, I'd have a little bit of a peak there, but otherwise it would mostly look like that. And then my initial phase is going to start off at 0. When I get to 0.1, it would drop down to minus 90. When I get to 2.5, it would drop down to negative 270. And then when I get to 90, it would drop down to minus 360. So my phase, yeah, I should draw the asymptotes first. I'm trying to do 2 steps at once, and I'm making a mess of that. Okay, first asymptote, sorry, all the way out to here. Second asymptote out to here. And third asymptote. Sorry, this is not the highest quality video. I've already done a couple of takes. I'm not doing it again. Oh, crap. I screwed that up too. The 0 should be up here at the top line. Okay, so at 90, sorry, at 0.1, we're dropping down to minus 90. At 2.5, we're dropping down to negative 270. At 90, we're dropping down to negative 360. And then I would pass through the middle of each of those at the frequencies that we're talking about. So it would look something like that. So that's a pretty decent sketch by hand. If I then wanted to verify that with Python, I would create the transfer function by taking n times the two denominators, since the denominators are actually 1 over. Let me make that explicit here. So here's n, here's den1, and here's den2. So I multiply those together, I get this thing. And if I create a frequency vector and an S vector and find GJ omega and then use my Bode utils module, which if you're curious is on my GitHub repository. I can find that for you if you comment and want it or whatever. Most of my students have it by now. And so that is pretty close to what we had drawn. And yeah, that's how you sketch a Bode plot. Find the poles. Make sure you find the poles correctly using the quadratic formula as needed to verify second order terms especially. And then at each first order pole, drop down your slope by minus 20 dB per decade and drop down your phase by minus 90. At each second order pole, drop down your slope by negative 40 dB per decade and drop down your phase by negative 180. Hope that's helpful. I will, for my students, well, I'll create a second video for the other half of this thing a little bit later. There's a second problem. Thanks.